was something from yesterday? Well, you were not. Everybody else was here. Okay, just one. Okay, just shortly recall. So, okay, so the idea is to give a formulation of Atiyah-Segal description of quantity theories, which somehow the idea is that you have some field theory, some d-dimensional manifold. The idea that to d-1-dimensional manifold you should associate a vector space, and to coordinates if you associate a state, so a vector in this vector space. And we want to do it in perturbation theory, particularly for gauge theories. And the idea is that then, since we use BD formalism, the homological way of reduction, to a boundary we should be able to associate a complex, and to the bulk we should be able to associate a vector in this complex, which is actually closed and defined up to. So actually a homology class in this complex. Okay. So what I explained yesterday is the BD formalism itself. The important point. So the BD formalism, we are on a here. So we are on a non-symplectic manifold. There is a canonical operator delta called the BD Laplacian, the square to 0, and it has these properties that delta exact half densities integrate to 0 on Lagrangian submanifold, and delta closed half densities have integral that is invariant under the formations of the Lagrangian submanifold. So these are the basic thing you want to do. So in the application to field theory, well, this delta closed density is essentially the exponential of the action in the functional integral, and the Lagrangian submanifold is the gauge function for the theory. Now the point is that well, choosing some, if you choose a reference half density rho, then you can define these delta on functions, and they still squares to 0, and I'll also assume that the reference nowhere vanishing half densities is also delta closed, which implies that delta applied on function has this property, where this bracket is the all-Poisson bracket associated to the all-symplectic structure. And now the point is that requiring delta of the function exponential of h bar s to be equal to 0 is equivalent to require s to satisfy this equation, where this is the all-Poisson bracket and this is delta applied to s. So this is called the quantum master equation, and it has a classical limit where you set this h bar to 0, which is the classical master equation. And yes, I focused first on the classical limit, is classical master equation, which is also the thing which makes sense without any problems, also in the three-dimensional case of field theory. Whereas well, this part, of course, is problematic because this BD Laplacian requires some choice of measure, which is what you don't have in field theory before you start doing some regularization. Okay, so this was the first thing. This notation I used, I called Q the Hamiltonian vector field of S, and then the classical master equation is equivalent to the condition that Q recommutes with itself. And then, okay, spend some time explaining what happens if you want to break this equation, because the problem is that, well, you apply this to field theory, S is local functional, and the RAM differential is essentially defined in terms of functional derivatives. So when you do this computation, you have to integrate by parts. And so if you want to apply this to field theory on a manifold boundary, this equation is broken. So I just study from simple algebraic point of view what happens if this equation is broken. So the idea you define an even one form of degree 0, which measures the failure from this equation, and just apply a little bit of Bertrand calculus, and it turns out that the associated two form, so the differential of this one form, this even two form of degree 0 is invariant under Q, and in particular it's even Hamiltonian. Okay, and then well, with this addition, this equation that says that you apply Q twice to the original odd two form, you get this function. So somehow this equation tells you how the classical master equation is violated. And then the point is that it's nice to work with non-degenerate two forms, so I'm going to the quotient. So I assume that the quotient by the kernel of a check is a smooth manifold, and I also assume for simplicity that the one form is also basic. So now on the quotient we have an even one form alpha boundary, and it's differential, as a closed to form, which is now also non-degenerate, and the vector field Q also descends, it's projectable, so you have a vector field on the quotient, and it's still decommutes with itself, and it's still Hamiltonian by its function as boundary. So we immediately come to this, more or less the conclusion. Yes, then we the summary. So we start with the quadruple F omega SQ. F is a supermanifold, omega is a non-symplectic form, S is an even function, Q is a non-vector field that Q commutes to itself. And out of this data, we produced, first of all, this other quadruple, where essentially it's the same structure, but now omega is even, S is odd. And now S is really the Hamiltonian function for Q, and Q commutes with itself. And in addition, we have a relation between the two things, because we have a projection map from this F to that F boundary. And now we have this equation that measures the failure from the fact that, so we know that S is not the Hamiltonian function for Q, but the error is a pullback of the one form on the boundary. So this is now the end of the construction. And I mean, one simple incarnation, so this can be done for every starting point. You can do the assumption made that this quotient is smooth, and you can do it also for field theory. And usually, well, if you want to do it explicitly, there is some construction. You really have to construct this one form alpha check, take its differential, compute the kernel, and do some quotient. So this requires some work. There is a nice class of theories where this is very, very simple. These are so-called AKSZ theories. These are a particular class of topological field theories where basically you don't have to check anything. Everything works, and somehow you have some sort of a hierarchical principle for which somehow these data, these boundary data, are constructed exactly the same way as this data, but integrating on a lower dimensional manifold. And this AKSZ theory also have a translation in the formal PTVD formalism that Damian Kalak showed. Okay, and actually in the example I will present you a very simple example of AKSZ theory. Okay, so the only remark, which is important for the second part, is that if you see what is important for the quotient is a two-form omega boundary. So this means that in particular you might want to change alpha boundary by an exact one form. But if you do that, you of course you have problems here, but you can resolve the problem by changing S. So basically you have a natural transformation, gauge transformation. You change alpha boundary by the differential of a function, and S by minus the pullback of that function. So, okay, and now let me rephrase what I explained yesterday. If you have a field theory, this means that the local field theory, then your BV data are the following. So the dimensional menu is fixed, but then what you have is that to a manifold M, you associate a triple F omega S with index M, which satisfy the axiom. So F is a supermanifold, omega is a non-symplectic form, S is a function, that's an even function satisfy the classical master equation, and everything is local. For example, the fields are local objects, like function or section and the action is an integral of the manifold of a density that at each point depends on finitely many jets of the fields. And omega is also local, and in particular Q turns out to be local. So then if you have a manifold with boundary, you just take, well, the definition which works in most examples is to define Fm as just essentially take the same definition but apply to manifold with boundary, and you use the same definition for omega, S, and Q. The problem is now that S is no longer the Hamiltonian factor for Q because of boundary terms. And then you just apply the construction, and you construct this quadruple F boundary, omega boundary, S boundary, Q boundary. The important point is that you know that this equation is satisfied up to boundary terms. So in particular, when you compute the kernel of these two form omega check, in it you will see essentially all the bulk field. So the result is that this F boundary, or this F boundary here, in particular, depends only on the fields at the boundary and their jets, their transversal jets. So for this reason, I will use the notation F boundary boundary M. So the idea that if you take two different manifolds with the same boundary, and you put the same theory, but you put the same theory on two different manifolds with the same boundary, the boundary structure, this F boundary boundary M, is exactly the same. This doesn't see the bulk. So it only sees the fields at the boundary and their transversal.
Not even the first order normal directions.
In the normal direction, yeah.
It does not see them.
It does, yeah. Yeah, it does finitely many transversal jets. The fields at the boundary and finitely many transversal jets. And for first order theories, yeah, it depends on the order of the theory. Sometimes you only see the fields at the boundary, the fields at the boundary, and the first order jets. You can see higher order jets, but only jets at the boundary. So it's a local information at the boundary. Okay, so that's a consequence of locality.
Okay. So is it possible you have the same boundary embedded in two manifolds?
Yes.
Such that some of the embeddings are non-equivalent.
What do you mean equivalent?
In algebraic geometry, that means that the normal bundles may be topologically equivalent, but not algebraic.
Okay, yeah, but this is not
here.
Yeah,
so if you look at higher order difference, there's no invariant that can distinguish these any term.
No.
You can always call her.
Yes. Yes. Yeah. Okay, and okay, maybe one example. So maybe, yeah, the example, yes. So maybe this point to make an example. Suppose we want to study Maxwell's equation. So Maxwell's equation. Well, we have one field which is the one form, the potential, and the equation adjusts at d star dA equal to 0. So there is a metric on your manifold as part of the data, and so you're using the metric to construct a Hodge dual of the differential, and Maxwell equation adjusts d star dA equal to 0. And I prefer to use the first order form as if it's equivalent, but simplifies a little bit the notation, so you can do everything in one transparency. So the idea is to introduce an additional field, d minus 2 form B, and to write the action function of b equals dA plus 1/2 b star b. And if you look at the critical, Euler-Lagrange equation for this action, you see that you have two of them. So if you take the variation with respect to b, you have the equation star b equal to dA, and if you take the variation with respect to a, you have the equation dB equal to 0. So from this you see that b is completely determined by a, and the equation for b gives you back this equation. So classically, this is equivalent to the Yamin's action. This is called first order formalism. And now, okay, you can do what I explained yesterday. You have to get the DB solution. What you have to do is to add terms. Well, you have to introduce generators for the Lie algebra that act on this space. So, I mean, the symmetries here are just, you can change A by an exact form. So the Lie algebra of the 0 form, so C is a 0 form. You give it cost number 1, and then you just extend the action by pairing these, well, this is essentially the Chevalier-Islander differential. You pair it with the conjugate to A in the symplectic form. So A plus, for me, the conjugate to A. And that's it. And then what you do, you can make the exercise to go to the boundary, see what is left. So essentially the point is that you see in the boundary you have this, well, the point is, you see you have this derivative here. So when you integrate by parts, these are the terms that you see on the boundary. So it turns out that after you do the reduction, the only fields that you see on the boundary are the restrictions of the fields A, B, A plus, and C. So these are the coordinates of the space F boundary. And the one form on the boundary is essentially what you get from here, just replacing the Ram differential with the variational differential. And you can, yeah, you can compute also what is Q on the boundary what is this boundary fraction. And interpretation is what you expect. In particular, you can compute this Q on the boundary. So this Q on the boundary has these two non-trivial components. One is dB and the other one is dC. And the interpretation for this is that, well, this is an equation. This tells you that on the boundary you have to impose a constraint dB equal to 0. And this other equation tells you that you have to work modulo gauge transformations. So this tells you that basically what we're describing on the boundary is this form symplectic manifold. You have the potential A and the D minus 2 form B that are just paired together by the symplectic form. And you go to the locus of the equation dB equal to 0. This is a Gauss law, which, well, you should think of this dually, this BD minus 2 form is essentially the electric field. And this equation dB equal to 0 is another way of writing down the equation. The divergence of the electric field should be 0. And you mod out the potential by gauge transformation. So this is a Marsden-Weinstein reduction. Okay, but instead of doing the reduction, we just stay at this level. Like we have these additional coordinates and this cohomological vector field Q, which is the same information. Okay, now I can move to the quantization. So, the part of this construction. So remember, we start with this space F. This is a space of fields, and out of it we produce this space of boundary fields, which is symplectic. Okay, so this is a classical theory. So to the boundary of a theory we associate a symplectic manifold. And now we want to quantize. So to quantize, we have to produce a vector space out of it. And okay, there is this general construction which is called geometric quantization that tells you how to produce a vector space out of a symplectic manifold and a certain additional structure. So the additional structure is a choice of polarization. The polarization is an involutive distribution on the symplectic manifold with Lagrangian leaves.
I somehow missed the logic. So you were explaining yesterday that in the classical field theory you need to view the fields. So you don't really reduce to the boundary, right? I mean, somehow you're you were integrating along pre-images of.
Yes.
So why do now geometrically quantizing only the symplectic guy, which is the boundary terms? Why aren't you doing anything for the pre-images?
That will come. Yeah.
Oh, that will come later.
Come, yeah,
so it's like the first stage is with.
Yeah, this is just the first stage of the. Yeah.
Okay.
Yes. So okay, so the idea is that you have this polarization, but which, well, not necessary. So this is an assumption that your symplectic manifold admits a polarization, which is involved in distribution with Lagrangian leaves. And the idea is that you should think of the vector space you want to associate to your symplectic manifold just as the functions on the leaf space. And actually, well, if you know geometric quantization, you know what format, but now I'm making a very crucial assumption to simplify the talk. I assume, well, that we have this polarization, that the quotient is moved, and actually basically making the assumption that our symplectic manifold is a cotangent bundle. Not canonically, but okay, assume that this F boundary is a cotangent bundle of some other manifold. Of course, in field theory, everything is infinite dimensional. The point is that, of course, typically this F boundary is actually, in field theory, is an affine space. So this is not a very strong assumption. Of course, the way to realize it as a cotangent bundle is not unique. I mean, you have such an affine space where you just given a vector space, a symplectic vector space, and you have to choose the splitting into Lagrangian subspaces. This, of course, is not unique. So this is the choice. And so make a choice to write your symplectic manifold as a cotangent bundle. And the important assumption is also that I want so here we have the one form, alpha boundary, and I want alpha boundary to vanish on the fiber. Okay. So this is well, this simplifies geometric quantization, And the idea is that, as I explained before, you can change this one form by an exact term. So the idea that you choose this exact term to adapt it to your choice of the potential marker.
Your pre-quantum line bundle is also trivial. Is this an additional assumption, or is it something that's actually built into it?
No, this is an additional assumption.
So no Keller potential?
No. Now, this is, now we are making the most drastic assumption to simplify the talk. And the point that, well, if you really want to apply this to field theory, these drastic assumptions are usually satisfied because you really are working with a fine spaces. If you want to do it more general, of course, these are assumptions, and because there's some very interesting geometry behind it. Okay, now I make another assumption, is that, so you see, there is a, now, okay, sorry. Now, of course, I can project down this to B, so I can compose, in particular, I have a projection from the bulk field to my chosen basis of boundary fields. Okay? And okay, let's say suppose I work locally, so I split this sequence, so I write F as a product Y cross B. And so notice that, so this B is my choice of boundary fields that I choose the basis. This Y contains both the bulk field and the cotangent fiber. Okay? Now the crucial assumption, which is, this is very important to go on, and if this is violated, well, we don't know how to go on, so this is always a quantizability condition. The crucial assumption that I want the symplectic form here, right, is a odd symplectic form here, to be compatible with this splitting. So the condition is essentially I have a non-symplectic form omega y, okay, omega, on the y factor, and the symplectic form over f is just the pullback. Okay, so in particular, so essentially I have a two form over y, so it has no component on b, and it does not depend. Now, if you think in terms of degeneracy, there is something weird here, right? So, yeah, unless b is zero-dimensional, then you may say that, okay, you want omega to be non-degenerate here, but then it will be necessarily degenerate here. Okay? So actually, this is the case. That's why I also dropped this condition that this omega should be non-degenerate. Actually, what I explained yesterday doesn't require this assumption, so this omega may be degenerate. The only important assumption for quantization is that this omega on the fiber is non-degenerate. Okay? Because essentially what we will want to do will be do some PV integration over the space y. So we want this omega to be non-degenerate, okay, but of course it's put back to f may be degenerate. And this is actually what happens in the finite dimensional case. If you go to the infinite dimensional case, where this f, y, and b are spaces of fields, then actually it may happen that both omegas are non-degenerate in the weak sense. So in the infinite dimensional case, essentially the good way to define symplectic structure is to say that when you regard it as a map from the tangent to the cotangent bundle, you require this map to be injective, but not necessarily subjective. And it may happen, it actually happens in the example that omega is non-degenerate in this sense, and even though it's written in this form. Okay, so
what is why if are you assuming that assuming that B is flat? So its cotangent bundle is trivialized?
Yes. Yeah. I mean, okay. Either you make this local, or if you want to make it, well, okay, you can do choices. Either you think of this as a local description. Of course, if you want to make it global, you have to, we have strong assumption over this vibration. Yes. So you can either take this as a local picture, then want to go into details for the global one, or just think, okay, we are in this lucky situation, which is actually the case in field theory. But okay, the point that this splitting is not a real problem locally. Of course, a real problem globally, but I mean, for the global construction, I don't need to split this way. It's just, I mean, if I choose a splitting, whatever I write down becomes easier. Okay. What is, however, a very strong assumption is that omega comes from the fibers only. Okay, so this is an important condition.
So how can it be non-degenerate in the infinite case? Would it always kill tangent vectors to B?
Okay, no, well, I can tell you. So, okay, we give you the example. So suppose that your f, let me see, okay, we can give you the example that will come later on. Suppose that your f are differential forms. So suppose that 1 forms plus d minus 2 form on. Okay. Okay. Well, when we maybe if you wait, this will come as an example later on too.
Okay.
You can see, yeah. I mean, otherwise I should write down the example. Okay, so. But it's essentially the point that in field theory, this omega is written as an integral, right? It's local, and essentially, well, this B are really boundary fields. So basically, the point is that you don't see them in this. Well, since it's an integral, these things are a measure zero. I mean, it's something that you see the measure zero subset, just the boundary. So that's why it doesn't spoil the non-degeneracy. Okay. So now let's assume that we are splitting. Now the interesting thing that I can write down the important equation. So remember that we have this equation, delta Q omega equal to delta S plus the pullback of alpha boundary. This was the fundamental equation of the whole formalism. And now I rewrite it using this splitting. And the condition that alpha vanishes on the fiber. So in particular, if I look at the one form along the fiber, I see the differential of S along the fiber, and then I only see the contraction of Q with omega. I don't see alpha, because by assumption, alpha vanishes on the fiber. And in addition, since omega doesn't have base component, I only see the Y component of Q. So this is the one part of the equation, and the other one is the part in the differential in the B direction. And here I don't see the contraction of Q with omega because omega doesn't have B component. So the only thing I see is alpha. Okay. So I split this equation into these two equations. And in particular, remember that we have this equation implied that something like 1/2 double contraction of Q with omega was equal to the pullback of S boundary. Now, well, I can rewrite it using this splitting, but the only thing that I want to point out that now here you only see the Y component of Q. Okay. Now, this first equation tells you that now if I think of B just as a parameter space, and I focus on the fiber Y, the first equation tells me that S is the Newtonian function of Qy. It's not a Newtonian function for the whole Q, but it is a Newtonian function for Qy. And this equation really tells you, so this double contraction with omega is really the Poisson bracket of S with itself using this vertical symplectic structure. Okay. So now what we have is that, okay, what you see Q as the Y component and the B component. The Y component is Hamiltonian, and its Hamiltonian function is S, but S does not satisfy the classical master equation, and this S boundary is the error. Okay. Now, let me use the second equation, and for simplicity, let me assume that I've chosen Darboux coordinates. So I will call, here in the cotangent bundle, we'll call B the base coordinate and P the fiber coordinate, and assume that I have my F in the form minus P dB. In the canonical form for this cotangent bundle. Okay, so what does the second equation say? Well, it simply says that if I take the differential of S with respect to the base coordinate, I get the fiber coordinate P. It becomes a very simple equation. So notice that the assumption I made, that omega did not depend on the base, implies this condition, and this condition in particular tells you that the action S is linear in the base coordinate. And so this is also a very strong condition. Okay. So
Does this only work for first order theories?
no, no, no. So this is general, of course. Well, okay, it works only. Well, you have to check whether this is possible. For sure, it works for first order theories.
But alpha might be in a different form.
Yes. Yes.
Otherwise.
Yes. Okay, now let me also make this assumption just to simplify this discussion. I will go back to this later on. So suppose that our action is also, well, that we have some half density, some reference of density over y, and then we apply delta, well, in the y direction to s and this is 0. So I'm assuming that apart from the boundary term, s satisfies the quantum master equation. So satisfy at the same time the classical and the quantum master equation. Okay, now what I can do, we can apply delta y to the exponential of the action, use the property of delta, and in its compatibility with the Poisson bracket. This turns out to be just again the exponential of s times the Poisson bracket of s with itself up to this coefficient. Now, you see, we computed s bracket s, and we saw that this was s boundary, so we can write this equation this way. Applying delta to the exponential of s is the same as multiplying the exponential of s by s boundary. Now, let's go back to the other equation. So the other equation said that, well, the derivative of s with respect to the base coordinate was equal to p or minus p, the outcome of p, right? And the point is that, well, what is the derivative with respect to the base coordinate is up to factor of h bar, is the Schrödinger quantization of the momentum variable. See? Well, Schrödinger would quantize a p variable, the fiber of the tangent bundle, as minus h bar times the derivative of the base coordinate. It's just a standard quantization. So then we can write this equation by saying that applying p hat, so this is a quantization of the momentum operator, to s, we get minus h bar p. So notice that p here has two meanings. So this p here, this p hat here, is the quantization of momentum for this configuration space, whereas this other p here is a coordinate of the fiber y. Okay? So you should think of s is a function on f, so we now regard it as a function on y cross b, right? And then we want to quantize b. So our vector space will be functions on b. So we can think of f as functions on y, well, complete the tensor product, the vector space. Right? So this is a bit more general, like, well, we have now some parameterized quantization. We have the vector space tensor with some parameter space. Okay, and then we have this equation. So the quantization of p applied to s is minus h bar p. Okay, what is the advantage of this? Well, the advantage is the following. We have the function as boundary, which was a function of b and q, and right here. So this was a function of b and p. And the idea is that now we replace this p plus minus I h bar delta over delta v. So we transform the function as boundary into a differential operator. Okay? So this is just Schrödinger's quantization. Whenever you see a p, you replace it with a minus h bar delta of delta b, and the convention that we put all the derivatives to the right. So this is standard only. Okay? So you think of as a symbol of this operator. Now, if you do this, and you have this property, when you apply this differential operator omega to the exponential of the action, again, you get just multiplication by its boundary. Now, as a function. Okay? But remember that we had multiplication by its boundary also in this equation. So the right-hand side of the two equations are exactly the same. So also the left-hand side has to be the same. So which means that the exponential of the action is killed by this operator. So notice that this delta y is a differential operator on y. and omega is the differential operator. Okay? And the exponential of the action is killed by their sum with this factor which pass squared. Not one remark, I made the assumption that delta y of s was 0. Actually, this is not really necessary. So what I can do otherwise, when I compute delta y of the exponential, if I then assume delta y of s to be 0, I also have this additional term. Okay? So this is the complete equation. Now, what I can think is that, well, this equation should be satisfied in the boundary. So this means that these things, this Poisson bracket minus delta y s, is also something that is concentrated on the boundary. So this means that essentially I should have a function s h bar boundary on the space of boundary fields, right, which compute this. And this will be actually our original s boundary plus corrections in h bar. Now I can repeat the previous construction. Now I define omega as the Schrödinger quantization of this new boundary action, and then I recover again this equation. So you might think of this omega either as the Schrödinger quantization of this corrected boundary action, or an appropriate non-Schrödinger quantization of S boundary. And the things differ just by higher order in H bar. Okay, so now the idea is that this operator, this sum, h bar squared delta y plus omega, is an important operator we want to consider. We call it omega y. And now, this should be our homological operator. Now the point is that delta y squares to 0, we know that. Delta y and omega commute, because delta is a differential operator on y and omega is a differential operator on b. So they commute. But the problem is that omega might not square to 0. I didn't prove that. And actually this is not a theory. This is an additional assumption. To go on, you have to assume that this omega squares to 0. Otherwise, the theory is anomalous. And you know that not all quantum theories are nice. So this is a physical condition, that omega must square to 0. It's not a theory. This is an assumption. Now, under the assumption that omega squares to 0, then also this operator squares to 0, so this becomes your homology, your boundary operator. And so you should think of the physical space of states as the homology of the okay? And notice that, well, there's still physical states parameterized by y. Now, the interesting thing is the following. Suppose that we have our y here is a product of two odd symplectic manifold y prime y second. I can do this fiber with the integration, this dv push forward I explained yesterday, on the y second fiber. So that is, I will choose a Lagrangian sum manifold y second, and I integrate over it. So the result will be a function on b cross y prime. And well, essentially using what we proved yesterday, taking care of omega, it turns out that the result is closed with respect to the new omega operator. So this is the same omega plus delta on the y prime fiber. Okay? So this means that this equation is compatible with this fiber integration. And the other thing you can see is that if you change the Lagrangian, you deform the Lagrangian, the result changes by an omega y prime exact term. So the omega y homology is the important point. So in particular, this way you can make sense of Wilson normalization in the case of manifolds with boundary. And in particular, you can integrate out the whole fiber, if possible. Then at the end, you just get a function on B, so an element of the vector space H, which will produce a homology class for omega. And this homology class for omega is the physical state. Okay, so let me summarize this. So starting from a local DD theory, we have obtained something that resembles the Atiyah-Segal characterization of the theory. So the data are the following. So we are theory in D dimension, then to a D minus 1 dimensional manifold, we associate a complex, vector space, and this boundary operator. And to each D manifold, we associate a state that is a vector in this space. satisfy the modified quantum master equation. So the modified quantum master equation is the equation omega. Well, it's that. Now, the interesting thing is that gluing, well, you expect gluing to work, and that's how this some meta theorem, some properties, and you have to check when you really make sense of this by theory. The point that when you have a field theory, you have to make sense of delta, of regularization, but so the statement you want to prove is that gluing works. So gluing means that, suppose you have your manifold M is cut into two pieces, M1 and M2 along a common boundary. Then you can compute the state for M1, the state for M2. You can pair the states. And if you have some residual parameterization Y prime, well, you have to do something for that, because it might happen that your fiber Y prime for the good manifold is not just the fiber product of the other fibers. So, but the condition is just that they have to be related by some BV push forward. So we have to present now gluing in this homotopic version. Now the application for this is the following. Suppose you have some field theory. The idea is that you cut it down into simple pieces. You compute the state for the simple pieces, and you recover the quantization for the original manifold just by gluing the pieces and doing this reduction. Okay, so let me come to an example where I can also explain this fact. So the example is the following classical theory. So this classical theory is called a Billiam-BF theory. It has two fields. One field is a 1 form A, and the other field is a D minus 2 form B. And the action is just the integral of B dA. So D here is a dimensional manifold. So this is a D4. It's called BF because dA is the curvature. You should think of dA as the curvature of A, which is usually denoted by F. So this will be B times F. So this is a stupid name, but this is. Now this theory has symmetries. You see that you can change A by an exact form and B also by the exact form. So you have to take care of the symmetries. I don't do the other exercise, give you the answer. The BV action corresponds to the action, so is the following. Now you have forms of all possible degrees, and so this is the notation, but the BV action still has this form, BDA. So now see, A is a sum of forms of all possible degrees from 0 to top forms, and this shift by 1 means that the Gauss number, this additional Z grading, is the following. The Gauss number of the I form AI is 1 minus I. And for B, the convention, see the shift B minus 2, so the convention is that the Gauss number of the I form BI is D minus 2 minus I. Okay. So what you do here is to take the non-homogeneous form B, wedge the differential of the non-homogeneous form A, you select the top form and integrate. And by this rule you see that the top form has a Gauss number 0. So this action will have Gauss number 0. Okay. We just, one reason why do I have to introduce differential forms of all possible degrees, you see that here we started just with 1 forms and D minus 2 forms. Right? Then we have the symmetries. So I can change A by the differential of the 0 form and B by the differential of the D minus 3 form. So 0 form and D minus 3 forms are the generators for my D algebra. The problem is that unless D is equal to 3, you don't see exact D minus, closed D minus 3 form X trivially. Okay, so one way would be to take D minus 3 form modulo closed ones as your D algebra, so the action will be free. The problem is that this is no longer local. Right? If you take D minus 3 form modulo closed ones, this is no longer a sheaf. So to make it a sheaf, instead of taking the quotient, you think of, well, basically, yeah, you just go on with the complex. You introduce D minus 4 form acting on this minus 3 form by the differential. And so this way you don't have the quotient, everything becomes it's still local, you just have differential forms, and you have, well, this very nice formulation. Now, what else is going to the boundary? Well, since you only have BDA here, what you see on the boundary are just the restrictions of the field. You don't see the jets, just the restrictions of the field. So in this case, so this, well, I can tell you what is F boundary. So F boundary turns out just to be, again, the same differential form, but now on the boundary. Okay? And the one form on the boundary, up to sign, is just the canonical one form. Essentially, you have the pairing between these forms and these forms, just taking wedge product in integral. And so this would be the form. But now you see, well, like looks at this vibration. So these things are the differential forms on, okay, so let me see, first let me do this format. So on F, we have this symplectic form delta A, delta B. So this is all symplectic form of degree -1, integrated over M, and it is non-degenerate. Okay? Now, okay, let me see what I choose. Well, two natural choices for this B. So I can think of this B as the space of A boundary fields or the space of B boundary fields. So if I do this, so suppose that I choose B to be, let's say, the A boundary fields, then what is Y? Well, this Y becomes differential, well, we have, see, remember, we have two copies of differential forms, right? The one corresponding to A and the Y corresponding to B. Right? If I choose B to be the base fields, this means that basically I've already given the value. So here I should take, for A, I should take the differential form that vanish on the boundary. But I will consider this symplectic form over here, and this is still non-degenerate. See, this form is non-degenerate if I take all differential forms, but not non-degenerate if I consider differential forms and differential forms that vanish on the boundary. The pairing is still non-degenerate. So this is an example where this works. Okay, in the infinite-dimensional case. Okay, so you can compute what is Q, what is alpha of the boundary, and now you can choose the polarization. So as I told you, there are these two natural polarizations, the one in the B direction, the one in the A direction, and so the idea is to use both of them. So let me split the boundary of M into the disjoint union of two subsets, D1M and D2M. Okay, so one of them could also be empty. I mean, you can decide everything is the one boundary or everything is the two boundary. So my notation for the 1 and the 2 is just that on one boundary, or okay, also the one collection of boundary components, I use the D polarization, and the other one I use the A polarization. Now, since the one form I had, so let me write it here. So my one form was integral of B delta A. Right? So this says that of the boundary. Right? So with respect to this form, this one form vanishes on the fiber of the tangent bundle if the A's are the tangent. So this is correct for the on D1M. The problem is that on D2M this is not true. Right? This one form does not vanish on the fibers. So what I do, I add an exact form. So the differential of this function, integral of dA. This transforms B delta A into A delta B, and A delta B has a property that vanishes on the fiber if B are the codes on the base. So I have to make this transformation. In particular, this means I have to modify my action. So my action on the theoretic boundary is not only integral of BdA, it has this boundary term, B times A on the D2, on the two components of the boundary, second component of the boundary. Okay? So there is this additional thing. Now, what is B? Right, this base field here, these are the A forms on D1M and the B forms on D2M. Now I have to write this splitting explicitly, so what does it mean? This means that, okay, write my field A as the boundary part plus the bulk part. So this is the component B, this is the component Y. And the same for B. Okay, so my notation for fat A and fat B are the coordinates in this base B. Now, well, fat A and fat B are defined on the boundary, but this should be fields on the bulk, so I have to stamp them in some way. And it turns out that the condition that this omega does not depend on the boundary corresponds to the choice where you extend fat A and fat B discontinuously by 0. So they are supported only on the boundary. So we have discontinuous fields. Okay? Now, having discontinuous fields is not a problem unless you want to take derivatives. Okay? So remember that in the action we have B dA. Okay? So, well, in principle we should take derivatives. So there is no problem in the term fat B d dA hat. This term is okay. I'm not taking derivatives there. But there are problems in the term fat B d fat A. You have taken derivatives. So the point that I can integrate by part to get rid of this derivative. So I rewrite this up to signs as the integral of d hat fat A plus an integral on the boundary of d hat fat A. So here again, I no longer have derivatives on fat A. Okay? So this is an important point. Now notice that B hat, right, is splitting. So on the boundary D1M, I should only see B hat. So this means that the B hat vanishes on that boundary. So the only thing that I see here is D1M. So at the end, I can rewrite the action this way. So I have again the BF action, but now just for the Y part. And then I have these boundary contributions. So notice that one boundary contributions, the one with, let me see, this one, is because I have to adapt the boundary one form. And the other boundary contribution, this one, is there because I want to avoid derivatives on the flat field. But now notice that the result now is symmetric. Okay, now the point is that, okay, now I want to quantize this here, I want to do this functional integral. And now, well, in this theory, I have very, very simple because you see the series is quadratic in the field B hat. So B hat and A hat are the coordinates on Y. So what we have here is a quadratic theory with linear, with a linear term. And this precisely is the case where you can do Gaussian integration. So the idea that you want to take the exponential of this and do some integration in the hat and the hat. And so you have a quadratic term, a Gaussian term, and linear terms. Okay. So you know what the result is. The only problem is that, of course, this is this D is a generator. Okay. So the point that, okay, you have to do this gauge fixing, you have to choose this Lagrangian in the mini space Y in such a way that D restricted to the Lagrangian is invertible. Okay. So to do this, a simple way to do this is to use Hodge theory. Of course, you have to use Hodge theory on manifold with boundary. So the idea is the following: we pick a metric, an arbitrary metric on the manifold. To make things nicer, choose this metric to have product structure at the boundary. Now you can do the Hodge decomposition. So in particular, you can write forms, differential forms. So notice that A hat as a differential form that vanishes on one boundary component, B hat vanishes on the other one. So what I can do is to split differential forms into harmonic forms. So A and B are the harmonic forms, and alpha beta are the orthogonal complement using the metric. Okay. And now what I do is so this would be my choice for Y prime and Y second here. So Y prime are the harmonic forms, and Y second is just the orthogonal complement. Okay, and now I have to choose a Lagrangian submanifold of Y prime orthogonal complement. So what is orthogonal complement? Well, these are the exact and coexact form. As a Lagrangian, I choose the coexact form. Okay? And now what I have to do is I have to restrict the round differential to the co-exact forms, and it is invertible there. Yes?
But doesn't it map coexact to exact?
Sorry?
Doesn't it map coexact to exact?
Yes.
So what do you mean by invertible on coexact?
So, okay. Well, you have to project down orthogonally. So you start with the coexact form, you apply D, and then you project down. Sorry, you have to pair.
Pair.
Yeah, you have to pair. Okay, and now we can make the computation. So the computation of the Gaussian integral, now it becomes really non-degenerate Gaussian integral, will be some determinant part, which I call Tm, and then there will be some exponential of an additional term because of the linear terms. Now this Tm, as a very interesting interpretation, is up to coefficient, the Rademacher torsion of the manifold relative to its bounded D1m or its bounded D2m. The two Rademacher torsion are the same. In addition, there is some phase which you don't see from this formal point of view because, well, this is just this is a product of determinants of Laplacian. Right, so you have to regularize in some way. There is an easy way to regularize, namely to take a triangulation of your manifold with boundary, and if you do that, well, you end up having some finely dimensional integrals of products of finely dimensional determinants. The only thing you see that there is a phase, an important phase, which, well, we were not noticed before, but it is there, so this is some sort of analog of a native variant for this here. So the torsion, and you have a phase. And then you have this, what we call effective action, so this is the result of the linear terms in the Gaussian integration. And, well, you have two pieces. One is that basically when you restrict to y prime, so just a variable effect field with the y prime field, and the other part is this bilinear term that comes from the Gaussian integration. So this eta for me is the inverse of the Dirac differential in these Lagrangian subspace. So this is the final result. So this way we can compute exactly what the state is, and you can easily check that it satisfies the modified quantum master equation. Now the point is that we want to prove the gluing. So this gluing here, and well, you have two things to check. First, you have to check that this factor glue, and then second, you have to check that this effective action also glue correctly. Now the gluing of this factor, well, it's Hart theorem. We didn't do that. It goes back to works of several people, Kotsevich, Fishik, and so on. So this is actually the gluing property for the torsions of manifold with boundary. And it is a theorem, so that part is okay. And then you have to do the gluing of the rest. And notice that, well, you see, we have this factor y prime. So it is this y prime we left, that these are essentially the cohomology relative to the boundary. And so the point is that here, we see here on M1 we have cohomology relative to the boundary, on 2 we have cohomology relative to the boundary, and then we want to get the cohomology for M. And of course, you can imagine that Meyer-Vittoris is hidden inside this. And the point that, of course, you have to relate the absolute Meyer-Vittoris to the concrete Meyer-Vittoris that you get here by doing some Gaussian integration on the boundary. And it works. Now, the last important point, which is important also for the non-abelian version, is that we can compute the propagators on the glued manifold in terms of the propagator of the pieces. So the idea is the following. Well, so the propagator, the inverse of D, in the Gaussian theory, is also the same thing as the expectation value of the two-point function. And so the idea is the following. Well, on a single piece, you can compute the two-point function and the one-point function, and then you glue the things together. And so you can recover the two-point functions on the glued manifold out of the one- and two-point function on the pieces. So for example, I can compute the one-point function here, the one-point function here, glue, and this gives me one piece of the two-point function on the glued manifold. And if you do this explicitly, this gives you explicit formula for the propagators on the glued manifold in terms of the propagator of the pieces. So these are now the differential geometry, where they tell you that, I mean, the parametrics, I can write down the parametrics for the RAM on the glued manifold this way. So the parametric when the 2 points are on, so this line is a boundary, along which read. So the parametrics for the case when the 2 points are, say, in M1 is given by the parametrics I had before, plus some additional contribution that is the homology. And you can do the same. So maybe the most interesting piece is this one. I want to compute the parametrics on one point on one side and the other on the other side. What I have to do is I have to compute these two parametrices for the two pieces. Choose a middle point on the boundary and do this convolution. Plus the other term that depends on homology. So essentially I can write down the parametrics for the group manifold as a convolution of the parametrices of the pieces, plus term depends on homology. So this is an interesting result. And this also is the key point to prove the gluing formula for the perturbation of abelian BF theory. So let me tell you what is the idea. For example, one example is non-abelian BF theory. So here you think of A and B taking values into the algebra and this dual, and you really take the whole curvature here. So you have a piece BTA, which is what you had before, but in addition you have an interaction term BAA. So the idea that if you do, the idea that you perturb the Gaussian integral by this term, this means that you will have some trivalent vertices around. You have to compute all the Feynman diagrams. Now, why does the gluing work? Well, the point is that, erase. Okay, let me draw it here. Well, suppose that I want, so I have some Feynman diagrams on the manifold with boundary. So the manifold and they cut it into two pieces, M1 and M2. Right? And the idea is that essentially, well, if I cut it, sometimes I would see a propagator that goes from one side to the other. And because of the previous formula, I can think of it as a convolution of propagators. Okay? So this tells me that if I do the perturbation theory on the glued manifold, is the same as doing the perturbation theory on the two pieces with linear boundary vertices. But the linear boundary vertices are precisely the terms we had before. So this term here. Okay? So these are the linear boundary vertices, and they are exactly the thing you need for the glue. So this shows that basically whenever you take a field theory that is a perturbation of abelian BF theory with the same symmetries, gluing works. So let me do this. So what are the examples of this theory? Well, there are a lot of theories. One is in one dimension you have quantum mechanics as an example of this perturbation. In 3 dimensions you have Chern-Simons theory. In the case where the algebra is even dimensional and it has splitting. Another example in 2 dimensions, the Poisson-Sigma model. So all these cases are topological field theory, but there is also a non-topological example which is 2-dimensional Young's theory, which is essentially abelian BF or non-abelian BF theory plus a term B wedge star B with some Moich structure. So the gluing it works essentially just by this argument. Of course, it works for a gauge fixed theory. Now the question is, what about omega and so on? Well, that's an interesting part of the story. The point that you can compute this omega using this technology of compactified configuration spaces, and this produces for you an explicit construction of this omega and show that you have a solution of this modified quantum master equation, and it also shows that omega squares to 0. Of course, this is a bit sophisticated. Essentially, the same level of complexity as showing that Cold-Series star product is associative. Use the same technology. You use quantified configuration spaces. You go to the boundary. You consider boundary contribution. Essentially, this omega is defined by boundary contributions. Okay. Now, just to finish, there are other theories you can consider for more physical theories, like scalar field theory, spin field Young theory, and in a higher dimension. And in principle, they can be treated by this formalism. What you have to do, of course, is to check what the renormalization means, whether the gluing really works, and well, how is omega defined, whether it's really square to 0, and so on. But okay, it's just the application, the formalism is there. Maybe just like you mentioned that, of course, there is another interesting theory you might want to consider, which is gravity. And of course, the quantum level, we don't know exactly how to do it, but already the classical level, it is interesting. I mean, there are two classical equivalent formulations of gravity. One is the high Einstein-Hilbert formulation, where the only field is a metric, and you have the Einstein action. And this works quite well in this formalism. However, there is a geometrically nicer formulation, which is called Palatini or Palatini-Cartan, where you have two fields. One field is the connection, and the other field is a coframe. And then you have one of the other Lagrange equations tells you that the connection is compatible with the coframe. So it turns out to be, it must be Levi-Civita. And then there is a second equation that tells you that, well, you get Einstein equation for the metric constructor out of the coframe. Nice thing is that if you do this up to 3 dimensions, it's very nice. It's easier to work with an Einstein-Hilbert formulation. If you go to 4 dimensions, apply the naive construction, you don't get the correct boundary theory. In the sense that you don't get, you have this boundary BFE structure, and it turns out not to be smooth, and also not to describe the correct symplectic reduction. So to make this work, you have to define the space in a nicer way. That's, I mean, we hope it can be done. We are more or less, we have a proposal. We have tried to finish the computation, but this shows that this theory is a bit more sophisticated, already at the classical level. Okay, so I think I can stop here. These are the main references for all this, and okay.
So all the theories you're considering are perturbations of healing BF theory.
Well, yeah, here yes, but in principle, yeah, the formalism is more general. Yeah.
So
For the quantum part, we did the computation for perturbation of the
what
field.
about perturbations of abelian transients?
Yeah, that's well. The point is that well, you have to choose a polarization.
Right.
And right, well, this polarization does not work, so we have to make some other choice. And well,
There's no canonical.
there's no canonical one. No. I mean, that would be the next exercise. And the interesting point is that when you want to do the gluing, the gluing works very well if you have transversal polarizations. So you choose different polarization. If you come from one side to the other, you choose them to be transversal. And then the gluing is particularly simple. So if you want to do Chern-Simons, not only do you have to choose a polarization, but actually you should try to choose a pair of transversal polarizations.
So I had a second question. When you did the Schrödinger quantization of the boundary action,
Yes.
So that's a first order operator.
No, because the boundary action is not linear in the P.
Why?
The boundary action is not necessarily linear in P, in the final coordinates.
But it is the first order.
No.
No. Anyway, so what kind of functionals can you act with that operator on?
Yeah, okay, that's an interesting question. The answer is a bit complicated. Let's see. Okay, for this kind of theories. So the first approximation, you would say that since perturbation of the theory, what you do is you see you have these boundary vertices. So basically, what you should think is that the functions of B you consider are multilinear functional of the boundary fields. So you have your fields placed at different points times some distribution. Actually, this can be some smooth form. This is only the first order approximation of it. because when you try to define this omega, it turns out that this produces extra terms, so you have to, well, write down. It is a bit sophisticated, actually it's quite interesting. Actually, well, there is an important point is, let me mention this. You see, we have this property that says that delta S, delta S with respect to B is P. So that's the crucial thing, right? In particular, you want to compute the exponential, right? The derivative of the exponential of S and the and this is important you want to do it. In particular, you want to do this even if you take the integral, if you take the functional integral. And the point that, well, when you take the functional integral, you would like to have this functional derivative outside. Now, if you're doing the first order functional derivative, it's okay. But if you want to take higher order functional derivatives, and you do this too naively, well, computing the functional derivative inside is not the same as computing it outside. So to make this correct, you have to introduce so-called composite fields, in the sense that you should think of powers of the variable b at the same point as a new field. And you should think as higher order functional derivative at the same point as first order functional derivative of the composite field. So if you define things this way, in terms of the combinatorial Feynman diagram, you get something which is well defined and in such a way that this omega works well. But then it turns out that again the space of function you have to consider is now more complicated. So essentially is multilinear operator of the composite fields. So at each point you can have a power of your field as a new kind of field. So you have to enlarge the space of fields enough to accommodate everything. So this would require the other 20 minutes of work.
Okay, thanks again.